Hey everybody, I hope all of you are doing fine. Today I just wanted to dive into a new topic, so to say. All right, this is kind of a pivotal video. We have finished the first part of the course, and that part is on forces and whatnot. And now we're going to a new part of the course, and that part is really the study of energy. All right. So far we have described motion using quantities that change. All right. We've described motion using position, velocity, and acceleration. All right. And basically, Newton's laws told us how these quantities change. All right. So we use Newton's laws to explain to us why these quantities, position, velocity, and acceleration, looked the way they looked, so to say. All right. Forces were the explanation of a change of motion, basically. So now we're moving to describe motion using quantities that don't change. All right. We're going to use quantities that don't change. And these quantities have a special name. All right. These quantities are called conserved quantities. All right. Conserved quantities. All right. So examples of conserved quantities that we'll see is momentum, energy, mass to an extent, and so forth and so forth, and so on and so forth. And we'll begin today with momentum. Although we actually won't get to momentum in this video or in the second video. But anyway, here we go. In this section of the course, we'll analyze collisions. What's a collision? This is a short interaction between objects. All right? A very short interaction between objects. Examples would be a soccer ball and a foot. I would say maybe ping pong. You know, when the ball hits the bat, that's pretty short. A pretty short interaction. Another example would be golf stick and golf ball, or even, let's see, two pool balls. All right, so like those balls on the pool table, and so on. So basically, I'm using the word short here, right? I'm calling a collision a short interaction. Now, what does the duration? That shortness of interaction? What does it depend on? Like, what does the duration of a collision depend on? Well, I'd say for today, we'll say the material of both objects. All right. The harder the material, the quicker the interaction. All right. I can give you some examples. All right. A soccer ball and a soccer player's foot, interact for only 20 milliseconds, which is a very, very short amount of time. All right. let's see. And the one that surprised me is the balls on the pool table. All right, balls on the balls on the pool table interact for only 1 millisecond. All right, so yeah, that's yeah, so that's really just to give you some context around what we want from a collision. Because in this section of the course, we'll really be trying to understand collisions. So anyway, there are two types of collisions. We have elastic collisions and inelastic collisions. All right? And you can think of elastic collisions as let's see, collisions that cause objects to deform. Cause objects to deform, but return to normal shape after the collision. All right? And this is normally done very quickly. All right? It's like, it's done so quick. And then in elastic collision, cause objects to deform permanently. All right. So to start this section, we'll study elastic collisions. All right? And there's a lot more to these, to the differences between elastic collisions and inelastic collisions. But as we go on this week and into next week, or you also have a quick exam on Tuesday, as we go on into the following weeks, we'll add more into our energy toolbox to really separate these definitions of collisions. All right? So, okay, let's keep moving. So let's look at one of our earlier examples that I mentioned, yeah? I was talking about a soccer ball and a foot, right? So basically what I mean when I say deformation is shown excellently by these three sequence of images, right? So before a soccer player kicks a ball, or at least at the moment a soccer player just hits a ball, like right there, he gently touches it, the ball is still in its original shape. And then when the soccer player, like this, and this is happening very, very quickly, this is milliseconds in time. So when the soccer player hits the ball, he exerts a force on the ball. All right? He exerts a force on the ball, and that force causes the soccer player and that force causes the ball to deform. All right? But once the soccer player's foot is away from the ball gets back to its original shape. All right? And what can we observe here? We can observe that elastic collisions behave like springs. All right? Elastic collisions behave like springs. So don't worry, we won't use Hooke's law in this section, but it's a very, very good observation, because for the ball to get back to its original shape, it has to, it's undergoing a restoring force, like how a spring would restore back to its original shape when it's been stretched or compressed. All right, it's just a good observation to make. So, yeah, we won't study Hooke's law, all right? I said we won't study Hooke's law, all right, for this section. Instead, we will study the impulse, all right? Now, what is impulse, all right? The impulse is a force, all right? Let me say this is a force that is exerted over a short period of time. All right, it's a force that's been exerted over a short period of time. Oh, I think when I was revising, I kind of already had some words here. All right. Anyway, so I then go to tell you. Well, we can start by looking how do we measure impulse, right? How do you measure impulse? I was rushing there. I apologize. So, just to backtrack, impulse is a force that is exerted over a short period of time. Now, how do we measure it, right? Well, we can look at a force versus time graph to do this. So back to our example of a soccer player and the ball, right? We can analyze how much force is being exerted in the same amount of time that the ball and the foot are in contact. So look, here I have about 800 newtons. So, okay, sorry. Let me start again. I have about 800 newtons of force when the ball has been compressed to its fullest. All right. Here, when contact begins, I can see I have 0 newtons of force exerted. At maximum compression, I have about 800 newtons of force. And at the point where the contact ends, I go back to 0, all right? And this is very, very fast, all right? Do you see this time scale is in milliseconds? And yeah, so this is basically how the curve looks like, how the graph of a force versus time graph looks like, right? And it can look like it can look like various shapes, but for this situation, this is what it for this situation, this is what it looks like. All right. So yeah. So now, yeah, you might want to ask yourself, how do we calculate the impulse? Well, the impulse is the area under the curve. All right. The impulse is the area under the curve. And how do we calculate this area? Well, we can do a math trick. All right. So the area, sorry, it's once more. I want to write it because I think that would promote retention. Anyway, the area basically under the bell curve can be made to seem like it's a rectangle instead of a bell. Like you see, we can put the area that was atop of the bell curve and bring it down while still keeping the same time constraints it had. All right? Like all we're doing here is just manipulating the geometry of the bell curve. And I'm saying bell curve because it looks like a bell. All right? So we can see that these shapes is really just the same shape over here. All right? It's really just the same shape right here. All right? So the area has not changed while the shape has changed. So that's why we're allowed to do this. That's why we're allowed to just bring the areas down and make it a definite shape that has a simple area formula. And that area formula of a rectangle really is just L times B, right? Area of a rectangle. Area of a rectangle is L times B. So in this situation, we have force on the y-axis and time on the x-axis, on the horizontal axis, if you like. So we can say that J is equal to force average times the time, times the change in time, times delta t. And there's our impulse, all right? That's our impulse formula, force times delta t. What other important analysis can we get from impulse graphs? Well, I want you this is just something to observe. Taller graphs means a larger force is being exerted. A tall thin graph means a large force has been exerted in a short period of time. And like a flat wide graph means a small a small force has been exerted in a large period of time. And you can have tall forces. You can have tall graphs that are wide as well. But when thinking about impulse, we're really only thinking about time in milliseconds. So we can't really talk about time in like that lasts like 10 seconds or so. We're really talking about a short amount of time when you think about that. So yeah. Anyway, so that's the impulse video. I'm sorry it's a bit late, guys. I gave you an incentive. If you watch these on time before class, I will increase your course grade by 2%. All right. I appreciate all of you, and yeah, I hope you watch this video. Bye.